Okay, we're going to be starting chapter 19 today, which deals with heat, work, and the first law of thermodynamics. We began this process by introducing ideal gases and gas phase processes in the last chapter. We're going to continue that today. So we're going to quickly review heat, work, and energy, which you've covered in your first physics class. Then we're going to get into how to calculate work done and on a gas. And then we're going to calculate work for ideal gas processes. And then this will all lead into the first law of thermodynamics, which is just a statement of energy conservation to include heat. Learning objectives, which you should be able to do after completing the unit. So back in 1150, you covered energy, mechanical energy, and that's just the sum of the potential and the kinetic energy of the body. And so that's due to the motion of the system as a whole governs its mechanical energy. And so the potential energy can be gravitational potential energy. Throw a ball up, kinetic energy goes into gravitational potential. It can be due to elastic energy, compressed or extended spring, or it can be due to electrostatic energy. And so the sum of all the potential energy and the kinetic energy of the system as a whole at the macroscopic level is what's called the mechanical energy. Then there's the thermal energy, and in addition to macroscopic movement of a body, the molecules and the atoms are all moving individually, and so if the kinetic and potential energies due to the bonds and the kinetic energy, that's all governed, that's all encompassed in what's called the thermal energy. And so the total energy of this system, which in this case would just be the rocket, is equal to its mechanical energy and its thermal energy. And so what we always need to be careful here is defining what's our system and what is our surroundings. And if there's no net work done on the system by the surroundings, then the energy of this system is constant. And so in other words, it can be converted to and from kinetic, potential, and thermal energy, but when we sum the total up, the energy is conserved, it's constant, if there is no net work done by external forces on the system. So quick review, how do we calculate work? Well, to calculate the external work is obtained by integrating the external force dotted with the displacement dr over the path. And this is what's called a dot product. And we're going to be doing that to calculate work. So external forces, since F external dotted into dr is equal to the magnitude of the external force times the magnitude of the displacement times the cosine of the angle between the two vectors, between the force and the displacement. Positive work is done when the force is in the same direction as the displacement. For example, you push on a box, that's positive work. And negative work is done when the force and the displacement are in opposite directions. And an example of that is a frictional force, which is in the opposite direction of motion. And so that's negative work that would be done by a frictional force acting on the object. And so here's, you should have done these at least in the first physics class. You did these energy bar charts. And so the initial kinetic energy plus the initial potential plus the external work done on the system must be equal to the final mechanical energy, kinetic plus potential, plus the change in the thermal energy. And so let's just do a couple examples here. So the first example is, suppose you pull on a rope and you lift a box up at steady speed, okay? So steady speed, the kinetic energy does not change because it's at steady speed, and so the initial and final kinetic energies are equal. So where is this external work, where is this going into? Well, it's a positive work because the work that you are doing, the force of tension is in the same direction as displacement. So that's positive work. And that work goes into raising the gravitational potential energy of the system, which is the box. Here's another example. You pull on a box and you drag it at steady speed. In this case, again, the kinetic energy is constant because it's steady speed. The gravitational potential energy is constant because you're pulling it across a horizontal surface. And so where is this work that you're doing on the system going? Well, it's going into heat. It's going into increasing the thermal energy because you're doing enough work to counteract the negative work being done by friction. And so in this case, the external work being done on the system goes into thermal energy. And so this shows here that energy can be transferred between the different forms, and it can be added to the system if work is done on it, external work. Now what we're going to do now is we're going to introduce heat. And so you can change the energy of the system not only by doing work on the system, but also by adding heat to the system. And heat is just energy. We're going to give it the symbol Q, and heat has units of joules. It's just energy that's transferred from a hotter body to a colder body due to a temperature difference. And so heat is not a property of the system, and therefore we don't define it with delta Q, but rather it's the transfer of energy from one body, a warmer body, to a colder body. And so we're going to add this term here, and so the generalized work energy equation states that the work done on the system plus the heat added to the system is equal to the change in the system's energy. So we can add energy, we can raise the energy either by doing work on the system, or we can raise its energy by adding heat to the system. And here's an example. So here's water. We can raise the energy of the water by heating the water, supplying heat, and we can also raise the energy of the water by doing work on the water. So in this case, the energy that the work that's being done to turn the paddle is dissipated as friction, by friction, and so that is used to heat the water. And they both have the same effect. They both increase the temperature of the water. It's just two different means for doing so. Okay. So we can either do work on the body or we can add heat. Now the most difficult thing I think to start with when we first start to deal with this is getting our sign conventions correct. Okay, so with heat, positive sign for heat means that heat is added to the system from the surroundings. And a positive value of heat, meaning heat is added, means a positive change in energy, which means that adding heat to the system increases the energy of the system. And when heat is removed from the system, Q is negative, and then delta E system is negative. Energy is lost by the system when heat is removed. So what's going on here? Well, at the microscopic level, heat is transferred because if you have a warmer body, the molecules are moving faster than they are in a colder body. And when you put them in contact and they collide, the molecules in the warmer body or the warmer medium transfer some of their energy to the molecules in the colder body or the colder medium, and therefore raise the temperature of the colder medium. So, space capsule returns to Earth, and it goes through the Earth's atmosphere. It gets very hot. Why? Has the capsule been heated? Or if not, what is the cause of the increase in the energy, the thermal energy of the capsule? So the answer is no. The capsule has not been heated. Heat is transfer of energy due to temperature differences. So what's happening here is the capsule goes through the atmosphere and friction does work on it, air resistance. So the air resistance, the force opposes the direction of the motion, and so that's negative work done on the system, and that has the effect of decreasing the mechanical energy and increasing the thermal energy of the system. And so in this case, work done on the system has the effect of increasing the thermal energy. So let's look at another example. Here's a gas, and you have a piston, and the gas is inside, and we place a piston on top here, and so the gas is enclosed. And suppose we insulate this cylinder very well. And we push on the cylinder, we apply an external force. Is heat added to the system, or is it removed from the system, or neither? And the answer, of course, is neither if the insulation is perfect, and in practice it's very close. So heat is not added to the system or removed from the system, and so Q is 0. Okay. However, work is done on the system because the external force is displacing the piston by an amount delta x. And so in this case, the force is in the same direction as the displacement, and so positive work is done on the system by the surroundings. In this case, the force applied to the piston. So if the heat Q is 0, no heat is added or removed, and positive work is done on the system, go back to our equation, Q is 0, external work is positive, that means that the energy of the system has increased, and that goes into thermal energy of the gas, which goes into raising the temperature of the gas. We'll see later that the thermal energy, at least for ideal gases, solely depends on the temperature. So higher temperature, more thermal energy, lower temperature, less thermal energy. Now, with gases, gases can be compressed, right? They're compressible. And so we're going to if we calculate the work here, so let's look at this gas here with a piston, and the pressure of the gas is trying to push outward on the piston. It's trying to push the piston outward. And so to keep the piston in place, there must be an external force applied on the piston that must be equal and opposite. And so recall that when the force and the displacement are in the same direction, work is positive, and when the force and the displacement are in opposite directions, the work is negative because force and displacement are anti-parallel. So if suppose the gas expands, so let's look at this bottom picture, the gas is expanding, is the work done, the external work done on the gas positive or negative? Well, the gas is expanding, and so dx points to the right. The external force trying to confine the gas is pushing to the left. These are anti-parallel, and so when a gas expands, the external work done on the gas is negative. And the work done by the gas, which is due to the pressure of the gas, which pushes outward on the piston, that's positive work because the force and the displacement are in the same direction. So when a gas expands, the external work is negative, the work done by the gas is positive, and so the external work is the negative of the work done by the gas. Now, if we want to put this work in terms of the state variables of a gas, pressure and volume, we can write that the force exerted by the gas, which is the negative of the external force, they're pushing in the opposite direction, is equal to pressure times the cross-sectional area. And so the work done by the gas is P times A, and the displacement is dx. Now, the area A times dx is just the change in the volume of the gas. And so we can write that A times dx as dV. And so the work done by a gas in expanding is equal to P dV, the integral of that, and that's equal to the negative work done by the external forces on the gas. And so now we have a new expression that the external work done on its gas by its surroundings is equal to the negative of the area under the pressure volume curve, the PV diagram, in going from initial volume to the final volume. And we see that if dV is negative, meaning the gas is compressed, then negative negative is a positive, and external work is done. And if a gas expands, dV increases. dV is a positive number, and that gives rise to negative external work, which makes sense because when the gas expands, it's in the opposite, the displacement is in the opposite direction as the external force. And so now if we have the PV diagram for a gas and as it's going through a process, we can get the external work done on the gas as equal to the negative area under the P versus V curve and going from V initial to V final. Okay. So let's do an example here. So in general, so to calculate work, we need to integrate this equation, and integration just means calculating the area under the curve. And so here's an example. If you're going from at constant pressure, if you're going from a volume V initial to V final, then at constant pressure we can pull P out of the integral, and the work done is negative P times delta V. And in this case, P is constant, delta V is just the V final minus V initial, and the area is just the square, the area under the curve. And so in this case, it's negative work done on the gas, which is equal to P times V final minus V initial, with a negative in front of it. So let's do another example here. So suppose you have a gas, and it's going through this process where it starts off at point A with a given pressure and a given volume. In the first stage of the process, it goes from A to B, so at constant volume, the pressure increases, okay, because the gas has been heated. Then it goes at constant pressure from point B to point C, So the pressure is constant and the gas expands. Okay. Then in the final stage, it goes from C to A, and here the pressure and the volume are both decreasing. And so the question is, what is the work done by the gas, which is the negative work done externally on the gas in each of these three processes? So let's calculate first as we go from A to B. Well, delta V is zero. The volume of the gas is constant, and so there's no displacement. And so here, the work done by the gas is zero, and the external work done on the gas is the negative of the work by the gas, and that's also zero. So from this point A to B, no work is done by the gas. Now as we go from B to C, the work done by the gas is the area under the curve and going from point B to point C, and the external work is just the negative of this. So if we go from point B to point C, that's equal to the area under the curve is 3 squares, 6 squares, 9, 12, 15, 18, 21 squares is the area under the curve. And each square has a height of 1 times 10 to the 5th pascals, and each square has a width of 1 times 10 to the negative 3rd meters cubed. And so the area of each square is 100 newtons times meters, and that's equal to 100 joules. So each square is 100 joules. The area under the curve and going from B to C is thus 2100 joules. And it's positive work done by the gas because the gas is expanding. Right? So displacement, expanding, means negative work done externally because the external force is in the opposite direction as the displacement. And it's positive work done by the gas because the pressure is pushing outward. So the force of the gas acting on the piston is positive. So plus 2100 joules is done by the gas and going from B to C, and the external work is negative 2100 joules. Okay, now let's go from C to A. Okay, in this case, the area under the curve is 3 squares, 6 squares, 9 squares, and then half of another 12 squares, because we can go up 4 rows, so that's 12 squares, and half of that is 6. So the area under the curve is 15 squares. Each square is 100 joules. And so, wait a minute, this should be negative 1500 joules because there's 9 full and 6 full, and so that's a typo. This should be negative 1500 joules, and the minus sign is because negative work is done by the gas because the gas is being compressed. So typo here, I will fix that. That's negative 1500 joules. And that since it's being compressed, positive work is being done on the gas by its surroundings. So to calculate the work done on a gas as it expands or compresses, it's just the area under the P versus V curve. And the external, if we're calculating external work, we calculate this area and then we tack on a negative sign. And if we're calculating work done by the gas, it's just the area itself. And I know these sign conventions can be a little difficult to remember, but the main thing is just calculate the area, PdV, If the volume increases, meaning the gas expands, that must be negative external work and positive work done by the gas. And if the gas is compressed, then the external work must be positive and the work done by the gas must be negative. So that's always the most difficult part, is just keeping track of your sign conventions. So what we found in the previous example is that if the volume of a gas is constant, meaning the process is isochoric, then delta V is 0, and then no work is done by the gas or on the gas. So W external, the work done on the gas, is 0, and the work done by the gas is 0. The second type of process, if the process is done at constant pressure, well, then to calculate this integral, we can pull P out of the integral because pressure is constant, and the integral of dV is just V delta V. And so at constant pressure, the work done, external work done on the gas, is negative P times delta V. And so if V final, again, is greater than V initial, delta V is positive, and the external work is negative, and the work done by the gas is positive. So in this case, constant pressure processes, the integral is very simple, and the external work is just negative P delta V. For isothermal processes, isothermal means constant temperature. In this case, neither the pressure or the volume are constant. And so in this case, the integral becomes a little more difficult. But for an ideal gas, we can use PV is equal to nRT, and we can express the pressure in terms of the other variables. So pressure is nRT over V. And so in this case, the work done by the gas, the area under the curve, is nRT over V times dV. Now, if it's constant temperature, and if the gas is in an enclosed container, then N and T are constants. We can pull everything out. And this integral of dV over V, the integral of that is equal to the natural logarithm of V evaluated at the endpoints. And so what we get here is that the work done by the gas is equal to nRT times the natural logarithm of V final over V initial. And then here it is in terms of the number of molecules and Boltzmann's constant instead of moles, and the ideal gas constant. So let's do an example. So suppose that we have 2 moles of a monotonic argon gas, and it expands isothermally, so constant temperature. So T is 298 Kelvin, and the initial volume is 0.025 meters cubed, and the final volume is 0.050 meters cubed. So what we want to do here is we want to calculate the external work done on the gas. So in this case, we were already given the equation. We have 2 moles. R is the gas constant, 8.31 joules per mole per Kelvin. T is 298 Kelvin, ratio of the volumes. And we get that the work done on the gas is equal to negative 3,400 joules. And so the work done by the gas must be positive 3,400 joules. Now, your book does not use external and gas. It does not use the subscripts once it starts talking about gases. It just uses a W with no subscripts. The book is referring to the external work done on the gas. I prefer these subscripts so we can keep track of whether we're talking about external work or the work done on the gas, because that affects the sign of the result. Um, so let's end today's lecture. We're going to end a little early because we went a little longer the last few days. So just a quick summary of heat and work. And so both heat and work can change the energy of a system. Work is mechanical. It's pushes and pulls. It's forces and displacement. Heat is adding or removing energy from a system due to temperature differences. And at the microscopic level, it's due to collisions. The faster moving molecules in the warmer body transferring energy at the microscopic level to the slower moving molecules in the colder body. Uh, Work is positive. External work, again, there's your book using just plain W again. It's W external is greater than zero when the gas is compressed, meaning energy is transferred into the system when an external force compresses a gas. So W external is positive. W external is negative when a gas expands, meaning work is done by the gas on the system, and that leads to a loss of energy from the system to its surroundings. Okay. Conversely, Q heat is positive when the environment is warmer than the system and energy is transferred in, and Q is negative when the system is at a higher temperature than the environment and energy is transferred out. And then finally, equilibrium. A system is in mechanical equilibrium when the sum of the forces is zero, or the sum of the torques is zero, so there's no net force or torques. A system is in thermal equilibrium when it's in the same temperature as its surroundings. So this is just a quick summary of heat and work. We're going to start on Monday with the first law of thermodynamics, which is energy conservation to include heat. And that's it. So have a great weekend, and we'll see you on Monday.